Good evening, ladies and gentlemen. Glad to have you here. This is the very last topic for IERS. It's called MSTP. If we remove the M, you can see it's STP. The M there stands for multiple. So we're going to learn about multiple spanning tree protocol, principles and configuration. It's quite a short topic because it majorly operates just like STP and RSTP, but with a few differences to sort out a few issues which we're going to look at. Okay. So rapid spanning tree protocol, RSTP. RSTP was an enhancement of STP. It allows for fast network topology convergence. So this was one of the major advantages of RSTP was fast network convergence. However, both RSTP and STP have a significant shortcoming. So the first one is all VLANs use the same spanning tree. So when all VLANs use the same spanning tree, it makes this impossible. You cannot be able to do VLAN-based load balancing. So we're going to show you these scenarios. So again, with a single spanning tree, once a link is blocked, it will no longer transmit traffic. So after we've disabled a certain port, if it's an alternate port, then it's on blocking state, it cannot transmit traffic. When it does not transmit traffic, it actually wastes bandwidth. And it can also cause failure in forwarding certain VLAN packets, as we are going to show you in a short while. Now, to improve the shortcomings of STP and RSTP, IEEE in 2002 defined a standard called 802.1s, which in full is referred to as multiple spanning tree. Multiple spanning tree. So, as you might have already guessed, while STP and RSTP were using a single spanning tree, now this one introduces a number of spanning trees, multiple spanning tree protocol. So MSTP equally implements fast convergence. In fact, when it comes to convergence, it operates similarly as RSTP, same. Port states, everything the same, and also provides multiple paths in order to load balance VLAN traffic. So we're going to understand some of those few things that we've read here in the forward. Now the objectives for this topic. A volunteer, please. Marvin.
Upon completion of this section, you will be able to be familiar with limitations of a single spanning tree.
Yes.
And understand the MSTP working mechanism. Yes. Basic MSTP configuration.
Configuration, exactly. So here, in fact, this topic is very short and very brief on matters MSTP, because MSTP is covered in detail in HCIE. So if you do HCIE, you're going to dive deeper into MSTP. So let's begin by looking at the limitations of a single spanning tree. What is the problem? What is the problem with a single spanning tree? So the very first problem is that some VLAN paths are unreachable. So let's explain that. What does that mean? Now, if you can look at this topology, we have LAN A and LAN B here, which have been configured to be on VLAN 2 and VLAN 3, respectively. Yeah? Now, as you can see here, you see, normally we have access switches, like here, right now, this is an access switch. Then the next layer is the aggregation. So that's why you're seeing they're arranged in this manner. Now, when that happens, when that happens, then again, we have a probability of a loop occurring between these switches. You see, a loop can occur. So in order to avoid this loop, we have to configure STP, RSTP. So those two for now. We have to configure STP or RSTP. Now, the other thing we need to do on these interfaces, so these are called uplink interfaces. What we have to do here is we have to allow between switch A and switch C and between switch C and switch B, these paths, we have to allow VLANs to pass through. So for example, between switch A and switch C, we've allowed pass VLAN 2. Between switch C and switch B, we've allowed pass VLAN 3 and VLAN 2. But now there's a problem. When STP or RSTP is done, when RSTP or STP that has been configured here is done, then switch A is elected as the root, and therefore all its ports will be designated ports and they'll be on forwarding state. Switch B will have to choose that particular port as the root port and this one as the designated port, because the root port offers the shortest path, root path cost to the root. Then switch C here has two ports, so one of them is blocked. So you can see this one is the root port, shortest RPC to the root. So it will be on forwarding state. But this particular link here, this one, it's gonna be blocked. It's gonna be blocked to avoid, to prevent a loop from occurring. So why were we saying that some VLAN paths are unreachable? So you can clearly see that after this has been blocked, then even though we've configured VLAN 2 and VLAN 3 to pass through this trunk port, it can no longer carry traffic. So in fact, data from VLAN 3 is not even going to be forwarded because this particular port is in discarding state. So that is one of the problems with STP and RSTP. Okay, so let's look at the other one. Now the other problem is about traffic load balancing. So we cannot load balance traffic. We cannot load balance traffic when it comes to STP and RSTP. Why? Because we are using a single spanning tree. Now we have the same scenario. But now, yes, we have VLAN 2 and VLAN 3, which are connecting to this access switch. Now, switch A is connected to an interface, a layer 3 interface that carries VLAN 2 traffic to their destination. On the other hand, switch B is connected. Switch B is connected to a layer 3 interface that is supposed to carry VLAN 3 traffic to their destination, for example. So you see, because this interface here has to be blocked, it means that we have to allow pass VLAN 2 and VLAN 3 on this particular interface. We have to allow pass for VLAN 2 and VLAN 3 on this particular interface. And see, now that is a problem. Why? Because this path is disconnected and it will remain idle. So we're simply wasting bandwidth. While on the other hand, this particular interface is going to be overloaded. It's going to experience congestion, for example. So that is problem number 2, that we cannot load balance traffic. Just give me a moment to respond to an urgent call here, and then I'll get back to you, please. Thank you. Okay, I'm back. I apologize for that. Okay, so can you hear me?
Yes, we can.
Okay, thank you very much. Okay, so the third problem with using a single spanning tree is that we cannot always select the primary optimal layer 2 path. So most of the time, it is the secondary optimal layer 2 path that is going to be used. So again, same scenario. So we have two LANs. We've configured them with VLAN 1 and VLAN 2 and VLAN 3 respectively on switch C there. Then, because this port is blocked, we've configured this trunk port between switch A and switch B to carry traffic for VLAN 2 and VLAN 3. Now, switch A is connected to a layer 3 interface that is supposed to deliver VLAN 2 traffic, while on the other hand, switch B here is connected to a layer 3 interface that is supposed to deliver layer 3 traffic to its destination. So you see, VLAN 3, the primary optimal path for VLAN 3 is this one here. When we are sending VLAN 3 traffic, the optimal path is to send it directly through this particular interface to switch B. Then switch B will now deliver it to the layer 3 device. So that's the optimal part. But because we're using a single tree and this interface is going to be blocked, now we have to use the secondary optimal layer 2 path. So that's the secondary. So those are the three problems that we encounter when we are using a single spanning tree. Now, let's look at some of the principles of MSTP, multiple spanning tree. Multiple spanning tree. So MSTP, multiple spanning tree. Now, while STP and MSTP use a single tree, MSTP uses multiple. It uses multiple spanning trees, each of which is referred to as an MSTI, or a multiple spanning tree instance. So each tree is called an MSTI. Now, each MSTI, or really, each MSTI uses an independent. Each MSTI uses an independent RSTP algorithm to calculate a spanning tree. So actually, as you're going to see when you do the configuration, most of the time the route for each MSTI might differ, thereby enabling the spanning trees to be actually different. So each MSTI uses an independent RSTP algorithm to calculate a spanning tree. Now, MSTIs are defined by an MSTI ID. They're defined using an MSTI ID, which is a 2-byte. It's a 2-byte integer. Meaning, VRP actually supports a maximum of 16 MSTIs. So you can create 16 different MSTIs. Now, generally, the MSTI ID ranges from 0 to 15. From 0 to 15. So an MSTI might have an ID of 0, 1, or 2, or 3, or 4, all the way up to 15. But by default, all VLANs are in MSTI 0. All VLANs are mapped. That's the word, actually. All VLANs are mapped to MSTI 0. So what you're saying here is this, VLANs, we have what we call a VLAN mapping table. Now, in this VLAN mapping table, it actually defines mapping between VLANs. It defines mapping between VLANs and MSTIs. So which VLAN belongs to which MSTI? Now, when it comes to VLAN MSTI mapping, you need to know that an MSTI can be mapped to one or more VLANs. An MSTI can be mapped to one or more VLANs, but one VLAN can only be mapped to a single MSTI. In short, a VLAN can only belong to a single MSTI. So it cannot belong to two MSTIs. But an MSTI can have multiple VLANs, can be mapped to multiple VLANs. Now, again, just to insist, MSTP, multiple spanning tree, is compatible with both STP and RSTP. And in fact, as you've seen, it actually implements RSTP in calculating its spanning tree. So it's no different. The port states, everything is simply RSTP. The only thing it's adding is the MSTIs. the multiple spanning tree instances, and the VLAN the VLAN mapping table, of course. Okay, so let me now explain. With that in mind, let me explain what is happening here. Now, generally, when you want to configure MSTP between switches, the first thing you have to ensure is that all the switches are actually in the same, what we call MST region, multiple spanning tree region. Now, a single multiple spanning tree region can contain multiple spanning trees. Each multiple spanning tree is what we call now a multiple spanning tree instance. Now, each instance is independent of each other, and the calculation process of each MSTI is the same as the RSTP calculation process. Now, if we look at this example here, we have two MSTIs. The first MSTI has an MSTI ID of 1. The second MSTI has an MSTI ID of 2. So we have MSTI 1 and MSTI 2. You can see that they have been color-coded with red and blue respectively. Now, we have 3 VLANs. We have VLAN 2, we have VLAN 3, and VLAN 4. Now, as you can see, VLAN 2 has been mapped to MSTI 1. On the other hand, VLAN 3 and VLAN 4 has been mapped to MSTI 2. Now, as you can see here, in MSTI 1, switch A has been selected as the root. You see, who becomes the root determines which port is blocked. And therefore, you can see that for MSTI 1, the port that is blocked is this one here. So that's the alternate port for MSTI 1. So any traffic that is supposed to pass through MSTI 1 cannot be able to be forwarded through this link here. So that's why all traffic from VLAN 2 will simply be forwarded like this. Because for VLAN 2 traffic, this port has been blocked. So I hope that is clear. Let me go ahead and talk about MSTI 2. So for MSTI 2, we've configured switch B as the root. So when we configure switch B as the root, then this is the alternate port. So this port here has been blocked. So traffic from VLAN 3 and VLAN 4 cannot pass through this link. It cannot pass through this link because that particular port has been blocked. So traffic from VLAN 3 and 4 has to pass through this direction. So generally, that is how MSTP works. That is how MSTP works. Multiple spanning tree protocol. Any question before we move on? Okay, so let's look at MSTP configuration. Now, MSTP can be used to sort all the problems that we initially looked at. All those problems with a single spanning tree, including being unable to load balance traffic, wasting bandwidth by blocking other ports, and therefore they're going to lie idle. Some links are going to lie idle. So MSTP is going to sort all those problems, as you've already seen from the previous slide. That even though a port has been blocked, it has only been blocked for certain VLANs, not for all VLANs. So no link is going to lie idle. Now, MSTP can be used to load balance internet access traffic of PCs from different VLANs. Now here, we want to create VLAN 1 to 10 and map it to MSTI 1. We also want to create VLAN 11 to 20 and map it to MSTI 2. So we simply want to create 2 MSTIs here. Now, the configuration example is on switch A. So how to configure MSTP? The first thing is you have to enable on system view. You enable STP like that. Then after that, you configure the mod, the STP mod. So STP mod, MSTP. Then after that, you have to enter the MSTP region configuration view by typing STP region configuration. Now, you have to give a region name. As I've said, if you want switch A, C, B, and D to operate the same STP, you have to give them all the same region name. They have to have the same region name. Now, it is in a region that you can create MSTIs. The command to create an MSTI and to map an MSTI to a VLAN is this one. So instance 1. So here we are creating MSTI 1. Then we are linking VLAN 1 to 10 to MSTI 1 like that. Similarly here we are simply creating MSTI 2 and mapping VLAN 11 to 20 to MSTI 2. Then we end with activating that particular region using the command active region configuration like that. So generally, it is the same configurations that you're going to make in all the other switches, I know you're asking yourself now, how do you specify who the root is? Because who the root is what determines the ports that are going to be blocked for each MSTI. So that is what we are looking at now in this next slide. In this next slide, we are simply choosing, so on switch A, we are simply making switch A the root for MSTI 1, and we are making it the secondary root for MSTI 2. So switch A is going to be the root bridge for MSTI 1. Then switch B is going to be the root bridge for MSTI 2 and the secondary root bridge for MSTI 1. So with that, then different ports with the root like that, now we can determine the port that is going to be blocked for each of the MSTI by actually increasing their cost. So here, for MSTI 2, we want this particular interface, G002, this one. We want this one to be blocked so that we don't have a loop here. So we want this particular interface on switch C to be blocked. So how to do that? We go into that interface, then we simply increase its cost. By increasing its cost, then its RPC to the root is going to be the largest, and therefore it's going to be blocked. So this is going to be blocked. How do we do that? The command is STP instance 2. Cost, we put 200,000. We put 200,000. So on the other hand, we want this particular interface, G002, this one. We want this one to be blocked when it comes to MSTI 1. So again, we go into that interface and increase the cost using the command STP instance 1 cost. Then we put a value there like 200,000. So the other command here, these are the ports that are connecting to the end devices. So just like in RSTP, we configure them as edge ports by using the command STP edge port enable. So you go into that particular interface, which is this interface that is connecting to PC2. then you use the command STP edged port enable. STP edged port enable. So generally, that is how you configure MSTP. That is the end of the configuration of STP. So we can always use the display command to verify which ports have been blocked, which ones are forwarding, and so on and so forth. So for example, let's go back to switch A so that we see where it is. So for switch A, this is switch A, and it's the root. It's the root for MSTI1, for MSTI1. So let's do the display command to see what we have there. So we can use display STP brief. So you see, you've always seen this column MSTID when you're doing STP and RSTP, and all of them were having a value of 0. And I told you at some point that I'm going to tell you what this means. So MSTID is actually the multiple spanning tree identifier. So by default, all ports belong to MSTID 0. But now we've created two MSTIs, MSTI1 and MSTI2. So you can actually see that for MSTI1, because because switch A is the root, you can actually see that all its interfaces, interface 1 and interface 2, are designated. They're designated ports and they're on forwarding state. On switch B, so switch B is actually the root for MSTI2. So again, you can see that because it's the root, all its interfaces for MSTI2 are on designated port role and on forwarding state. Okay, so we can also check the port status. So for example, on switch C and switch D, so switch C and switch D are access switches. They're the ones that are connecting to PC1 and PC2 respectively. So we can actually see that if we do display STP brief for switch C, for this particular MSTI, for MSTI2, then this interface G002 is actually blocked. It's an alternate and it's on discarding. On the other hand, for switch D, we can see that this one again, 2, is discarding because we increased the cost. So generally, that is how MSTP operates, by building multiple spanning trees. Ladies and gentlemen, that is the end of this topic. Asanteni sana. Can someone help us with the first question and another one with the next one? The floor is open. A volunteer. Anyone?
Do I take question 1 or 2?
Yeah, take one.
So one says, describe the limitations of a spanning
what
tree.
are the problems with a single spanning tree? So you can just mention them. You really don't need to explain them.
Yeah. Okay. So first off, it was said because of just the one the one spanning tree, sorry, I'm just thinking about both network convergence, which is one of the good things about it.
So can you move closer to your mic? We can't hear you very clearly.
Oh, sorry. Give me a second. So basically, it's some of the paths become unreachable.
Exactly.
Because of some of the paths become unreachable.
Blocked links. Blocked links do not carry traffic. So unreachable. Another one.
And then it's unable to load balance.
unreachable paths cause what we call secondary
Optimal layer 2 path.
optimal path. So
And then the
blocked links do not carry traffic. What's the problem with this? They waste bandwidth. They waste bandwidth because that link will just lie idle there. Then unreachable paths. Then another one, the last one now. What you said, eh?
Yeah, it can't load balance.
Cannot do VLAN based load balancing. Thank you very much, my brother. The next question, anyone? Which of the following statements about MSTP is false? Anyone? So let me try this. Can I get where is it? Okay. So which one is false? So I'll be calling each one of you. Let me start with Marvin. You're the one that answered that question, the first one.
Yes.
Okay. So Winnie, true or false? One MST region can have only one MSTI. Is that true or false? Winnie? One MST region can have only one MSTI. True or false? Okay, Macau?
False.
Yes?
False.
That is false. Very correct. So a region can have more than one. Each MSTI uses the RSTP algorithm independently. Winnie? Okay, Marvin?
True.
Very true. MSTP is compatible with STP? Macau?
Okay.
True.
MSTP is compatible with STP. Very true.
True.
Owen, are you able to answer the last one? An MSTI can correspond to one or more VLANs. That is, you can map an MSTI to one or more VLANs. Owen, can you enable your mic and tell us that? True or false? Yes, very true.
True.
Okay, asanteni sana, ladies and gentlemen. For sure, you're not going to miss a question on MSTP in your exam on Friday. So I wish you the very best in your exam. I hope you've revised enough and gone over the dams. I wish you the very best. Asanteni sana.